On the night of May 13, 2019, an infrared telescope on the summit of Mauna Kea in Hawaii was pointed at the center of the Milky Way. This was not unusual. Astronomers have been pointing instruments at the galactic center for decades. At its very heart sits a black hole 4 million times the mass of our Sun. The black hole is called Sagittarius asterisk. It sits 26,000 light-years from Earth, hidden behind thick clouds of gas and dust that make it invisible to ordinary telescopes. What it recorded over the course of that night was something that had never been seen before in 20 years of continuous observation of this object. Sagittarius asterisk brightened, not slightly. Not within the normal range of variability. It brightened by a factor of 75 times its normal luminosity. In less than 2 hours, the black. The paper was published in the Astrophysical Journal Letters. Its title was Direct, an unprecedented bright flare of SGR asterisk. The lead author described the brightening as so dramatic that at first the team thought they might be looking at a star, not the black hole itself. What caused it? This is not a simple question. It is not a simple answer. And understanding it requires understanding everything that came before, and everything that surrounds the black hole in the heart of our galaxy. Understanding why the 2019 flare was so surprising requires understanding what came before it. 2 decades of patient, systematic observation that built a picture of Sagittarius asterisk so complete and so consistent that a deviation from it was immediately recognizable as something unprecedented. The story begins in the early 1990s, when 2 independent groups, one in Europe, one in the United States, set out to track the individual stars near Sagittarius asterisk over time, using the precision of their movements to determine the mass of the invisible object they were orbiting. Year by year, the picture sharpened. Stars in the immediate vicinity of the galactic center were moving fast, measurably fast over a period of years. Their motions traced curved paths, orbital paths, ellipses whose focal points all converged on the same invisible point at the center of the cluster. The mass of this invisible object was calculated with increasing precision, approximately 4.15 million solar masses, concentrated within a region smaller than the orbit of Mercury. The only known class of object consistent with these properties was a supermassive black hole. The work of both groups was awarded the Nobel Prize in Physics in 2020. The citation recognized the discovery of a supermassive compact object at the center of our galaxy. But knowing that Sagittarius asterisk exists, and knowing its mass, is different from understanding how it behaves. And what 20 years of subsequent monitoring revealed was a source that was variable but bounded, flickering within a predictable range, producing occasional flares, but always staying within a known behavioral envelope. And then May 2019 happened, and the envelope was gone. The center of the Milky Way is not like the rest of the galaxy. Out here, in the spiral arm where our solar system lives, space is relatively sparse. Stars are separated by light years. The radiation environment is manageable. Toward the galactic center, all of this changes. The stellar density increases dramatically. The radiation environment becomes harsh. The gravitational forces approach the extreme. And at the very center of all of it, a black hole that has been there for billions of years, quietly dominating everything around it. Within the innermost fraction of a parsec, stars move at extraordinary velocities. One star, designated S2, orbits Sagittarius asterisk with a period of just 16 years, reaching a speed at closest approach of nearly 3% of the speed of light minus 9,000 kilometers per second. The S-stars provided the first definitive proof that a supermassive black hole exists at the center of our galaxy. Their orbits trace an invisible point of immense gravity. There is nothing else in physics that produces that kind of stellar motion except a black hole. Sagittarius asterisk, has a mass of approximately 4.15 million solar masses. Its event horizon has a radius of roughly 12 million kilometers, smaller than the orbit of Mercury around our Sun. What makes Sagittarius * unusual among supermassive black holes is how quiet it is. It is, by all standards, extraordinarily dim for its mass. The black hole at the center of our galaxy has been sitting there for billions of years, accreting so slowly that it barely registers against the background of the galaxy around it. Until, on one night in May 2019, it didn't. Tuandu arrived at the Keck Observatory on Mauna Kea with a specific observing program in mind. The observing run on May 13th was scheduled as part of an ongoing monitoring campaign. The specific focus was the aftermath of a close approach between Sagittarius * and a dusty object called G2, an encounter that had occurred 5 years earlier and whose consequences were still being investigated. The observing protocol was routine. Images of the galactic center field were taken through multiple infrared filters. The data reduction happened in real time. The first indications came within the first hour of observation. The brightness measurement for Sagittarius * was too high. Not dramatically, alarmingly high, more subtly wrong than that. Sitting slightly outside the range that feels right, the number that prompts a second look not because it screams error but because it doesn't quite feel like the usual. Do looked at it, checked the calibration, checked the sky subtraction, found no obvious error. The number was still too high. As the night progressed and more data accumulated, the picture became unmistakable. Sagittarius * was brightening, building, sustained, growing brighter with each successive exposure. By the time the source reached its peak, it was producing 75 times its median infrared luminosity. The peak lasted approximately an hour. During this time, Sagittarius * was so bright in the infrared that it briefly competed with the most luminous stars in the immediate cluster. Then it began to fade, but unlike typical flares, it settled not at the historical average but at a level noticeably above it. The spectral behavior of the flare added another dimension of anomaly. During the peak, the spectral index was different from typical SGR * flares, a slightly steeper slope, implying either a harder electron energy distribution, a different emission mechanism, or a more strongly magnetized emission region. What was happening near the event horizon of Sagittarius * on that night was not simply a larger version of the usual activity. It was, in some measurable physical sense, a different kind of activity. And figuring out what it was would take years. Black holes do not suck. They do not consume things that are not already falling toward them. The Sun, if replaced by a black hole of equal mass, would have exactly the same gravitational effect on Earth. Our orbit would continue unchanged. What makes black holes extraordinary is not their appetite but their extremity. They are the most compact objects in the universe. They curve spacetime so severely that time itself slows near them. They are the most efficient energy-converting machines in nature. When gas falls toward a black hole, it doesn't fall straight in. It has angular momentum, it is rotating, and this prevents a direct radial path. Instead, the gas settles into a rotating accretion disk. As material slowly loses angular momentum through magnetic interactions, it spirals inward, descending to smaller and smaller orbits. As it descends, the gas is compressed and heated. Magnetic fields are stretched, tangled, and amplified. Collisions accelerate electrons to relativistic speeds. The heated gas and the relativistic electrons both radiate, through thermal emission and through synchrotron radiation. Sagittarius * is not an efficiently accreting black hole. Its accretion mode is called a radiatively inefficient accretion flow, (RIAF). The disk is not thin, flat, and bright. It is hot, puffed up, geometrically thick. Most energy is ejected inward rather than radiated outward. Sagittarius Asterisk is not an efficiently accreting black hole. Its accretion mode is called a radiatively inefficient accretion flow, (RIAF). The disk is not thin, flat, and bright. It is hot, puffed up, geometrically thick. Most energy is ejected inward rather than radiated outward. Only a small fraction of the available gas supply ever reaches the event horizon. The vast majority is expelled in outflows at larger radii. This is why SGR asterisk is so faint despite sitting at the center of a galaxy full of gas. The black hole is surrounded by fuel it cannot efficiently use. The radiation from SGR asterisk is dominated by synchrotron emission from relativistic electrons accelerated by magnetic reconnection events, sudden, violent rearrangements of the tangled magnetic field that release stored magnetic energy and rapidly accelerate electrons to high energies. This is the origin of the normal flares. They are magnetic reconnection events, localized explosions of energy release that produce brief, bright pulses of infrared and X-ray emission. The May 2019 event was almost certainly a magnetic reconnection event, but one far larger than any previously seen. And understanding why it was larger is the central question. In 2011, astronomers analyzing infrared data from the Very Large Telescope noticed something odd in the crowded stellar field around Sagittarius asterisk. Moving through the scene on a distinctive trajectory was an object that didn't look like a star. Its infrared color and extended emission suggested it was not a point source, but rather a compact cloud of gas and dust, glowing as its surface was heated by the intense radiation environment of the galactic center. They called it G2. The prediction was dramatic. When G2 reached periapsis in 2013-2014, tidal forces would rip it apart. The gas would be stretched into a long stream that would spiral into the accretion disk, increasing the accretion rate and causing Sagittarius asterisk to brighten significantly, possibly by orders of magnitude. The astronomical community watched. Multiple telescopes coordinated. The event attracted global attention. 2013 came. 2014 came. G2 passed through periapsis, and Sagittarius asterisk did almost nothing. The explanation was that G2 was not simply a gas cloud, it appeared to have a compact stellar core that survived tidal disruption. The outer envelope was disrupted, the core survived, but G2 left something behind. The disrupted outer envelope created a trailing stream of material on an orbit that would bring portions of it back toward the black hole over a period of years. Could this delayed infall, arriving years after the periapsis event, be responsible for the 2019 flare? The timing is suggestive. Periapsis, 2014, the flare, 2019. The G2 material infall hypothesis is one of the leading explanations for the 2019 flare. It is not proven, but the timing is plausible, and the magnitude of the expected infall is consistent with producing a significant accretion event under some models. And G2 is not unique. There is a population of similar objects, G1, G3, G4, G5, G6, compact, dusty, on elongated orbits around Sagittarius asterisk. Their existence means the galactic center environment is more dynamically complex than was appreciated before G2's discovery. Episodes of enhanced activity may be more common and more varied than the pre-2019 history suggested. G2 was not the only object in the galactic center to have a close encounter with Sagittarius asterisk in the years preceding the 2019 flare. S2, the most famous and most precisely studied of the S-stars, reached its closest approach to Sagittarius asterisk in May 2018, 1 year before the unprecedented flare. S2 is a Bo-type star, massive, hot, luminous. Its mass is approximately 14 solar masses. it produces a powerful stellar wind. And its orbit is a tight ellipse with a period of 16.05 years. At its closest approach in 2018, S2 moved at approximately 2.55% of the speed of light, 7,650 kilometers per second. Close enough that the effects of general relativity became measurable. The gravity instrument at the Very Large Telescope Interferometer detected the relativistic orbital precession in S2's orbit, confirming that general relativity correctly describes the spacetime geometry around Sagittarius asterisk. This was a landmark result in physics, the first test of general relativity in the gravitational field of a supermassive black hole. As S2 moved through periapsis, it was depositing stellar wind material into the region close to Sagittarius asterisk. The timing is striking. S2's periapsis was May 2018. The unprecedented flare was May 2019. 12 months later, consistent with the expected infall timescale for material captured from S2's periapsis wind. Is this a coincidence? Possibly. But the S to periapsis hypothesis and the G to material hypothesis are not mutually exclusive. Both could have contributed. The galactic center in 2018-2019 saw a confluence, S2's closest approach in its 16-year orbit, and the expected arrival of G to envelope material. The confluence of events may have primed the system for the record-breaking brightness of May 2019. On May 12, 2022, almost exactly 3 years after the unprecedented flare, the Event Horizon Telescope collaboration held simultaneous press conferences around the world. They had an image to show. The image was of Sagittarius asterisk, the first direct image ever taken of the black hole at the center of our galaxy. A glowing ring of orange-amber light surrounding a dark central shadow, the shadow cast by the black hole itself, where gravity was so extreme that no photons could escape. The Event Horizon Telescope is not a single telescope. It is a global network of radio telescopes observing simultaneously and combining their data using very long baseline interferometry. The baselines approach the diameter of Earth, giving the HT an angular resolution of approximately 20 microseconds. This is equivalent to resolving a golf ball on the surface of the Moon. Imaging SGR asterisk was far harder than M87 asterisk. Its smaller size means orbital timescales near the event horizon are just minutes. During a single observing session, the source changes significantly, the plasma moving through multiple orbits while the telescope watches. New analysis techniques were developed specifically for this variability. The resulting image represents a time-averaged view, what the ring looks like averaged across many snapshots at different orbital phases. The image confirmed the ring structure and a dark central shadow whose size precisely matches the mass of 4.15 million solar masses. For understanding the 2019 flare, the HT image provided crucial physical context. The polarization structure of SGR** ring emission suggested a partially organized magnetic field near the event horizon, one that can store and release energy more efficiently in reconnection events than a completely disordered field. And the HT observations provided evidence that SGR* may periodically enter a magnetically arrested disk state, where the magnetic field near the black hole becomes strong enough to temporarily halt infalling material, building up enormous stored energy before releasing it in a catastrophic reconnection event. There is an instrument operating right now that can track individual structures orbiting Sagittarius * just outside the event horizon in real time, as they complete their orbits in 30 to 45 minutes. It is called gravity. It operates at the Very Large Telescope Interferometer in Chile, combining the light from all four of the VLT's 8.2-meter unit telescopes into an optical, infrared interferometer with a baseline of 130 meters. Gravity can measure the position of a stellar source in the galactic center to within 10 to 20 microseconds. During large infrared flares from SGR*, gravity detects not just the brightness increase but also a positional wobble of the emission centroid, tracing a roughly circular pattern, repeating on a timescale of approximately 30 to 45 minutes. This is the orbital period of material at the innermost stable circular orbit around SGR*. What gravity is detecting is a localized concentration of hot plasma, heated by magnetic reconnection, orbiting near the ISCO. We are watching material orbit a supermassive black hole at 30% of the speed of light in real time. The gravity observations establish the physical mechanism of large SGR* flares directly, discrete, localized plasma hotspots forming near the ISCO through magnetic reconnection, orbiting for one to several periods before fading as electrons cool. The unprecedented brightness of May 2019 corresponds to an exceptionally energetic reconnection event creating a particularly hot, dense, compact plasma blob, more luminous than typical flaring structures by a factor of 75. The elevated activity since 2019 corresponds to a higher than normal rate of such energetic events, the near-horizon magnetic field more frequently reaching the threshold for explosive reconnection. Infrared is where the 2019 flare was discovered. But the physics of magnetic reconnection and electron acceleration produce radiation across a wide range of the electromagnetic spectrum simultaneously. X-ray observations are the most directly complementary to infrared. When magnetic reconnection accelerates electrons to relativistic energies, the highest energy electrons produce X-ray emission through inverse Compton scattering, boosting lower energy photons into the X-ray band. The timing of any delay between infrared and X-ray peaks encodes information about electron cooling rates, magnetic field strength, and the size of the emitting region. In 2021, the community organized a major coordinated multi-wavelength campaign targeting SGR*. Simultaneous observations from Keck, Chandra, Nuster, the VLA, and gravity. The goal: to catch a significant flare at all wavelengths simultaneously. The campaign succeeded. Simultaneous infrared and X-ray data confirmed the physical picture of magnetic reconnection driving correlated emission at multiple wavelengths. The relative timing of the flare peaks at different wavelengths provided new constraints on electron cooling and emission geometry. Radio observations added a distinctively different piece of the picture. SGR** radio emission comes from a more extended region than the infrared, out to hundreds of Schwarzschild radii. Radio monitoring showed that the overall radio flux density of SGR* was modestly elevated during 2019 compared to earlier baselines, consistent with a broader change in the accretion state rather than just a localized near-horizon event. The coherent picture across all wavelengths, the outer accretion flow providing more material, more magnetic flux, more electrons, feeding an inner environment capable of producing larger and more frequent magnetic reconnection events. The question of what Sagittarius* did on May 13, 2019, becomes more significant when placed in its deep historical context. We know, from indirect evidence, that Sagittarius* has not always been as quiet as it is today. The most striking evidence comes from the Fermi bubbles, two enormous lobes of gamma-ray emission discovered in 2010, extending approximately 25,000 light-years above and below the galactic plane, centered on the galactic center. These structures are among the largest known objects in the Milky Way. The energy content of the Fermi bubbles is staggering, estimated at roughly 10 to the 55th to 56th ergs. This is millions of times the energy of a typical supernova explosion. The age of the structures is debated, but estimates suggest the activity that produced them occurred somewhere between a few million and tens of millions of years ago. What is clear is that Sagittarius* was, in the cosmological past, far more active than it is today. The transition from that active state to the current near dormancy represents one of the great phase transitions in the history of our galaxy. There is also evidence for more recent episodes of elevated activity on timescales of centuries, not millions of years. X-ray reflection from molecular clouds in the galactic center shows that Sagittarius asterisk produced a period of intense X-ray activity approximately 100 to 400 years ago, a luminosity roughly 1,000,000 times its current level. The 2019 flare, unprecedented in 20 years of monitoring, may represent a small echo of the kind of activity that was more common in the historical past. The dormancy of Sagittarius asterisk is not permanent, it is punctuated. Does any of this affect us? The short answer is no, not directly, not now, not on human timescales. Sagittarius asterisk is 26,000 light-years away. The radiation produced by the 2019 flare was diluted by the square of that distance to levels far below detectability without specialized instruments. There was no observable effect on Earth's radiation environment. No increase in cosmic ray flux. No impact on biological systems. The black hole 26,000 light-years away brightened by a factor of 75 in the infrared for a few hours, and nothing at all happened here. The longer answer is more interesting. The activity of Sagittarius asterisk, even at its current low level, is not entirely irrelevant to conditions in the galaxy around it. The cosmic rays generated by energetic events near the event horizon propagate outward and interact with the galactic environment. If SGR asterisk were to transition to a significantly more active state through a major tidal disruption event or the capture of a large gas cloud, the consequences for the galaxy would be non-trivial. An AGM-level SGR asterisk would produce radiation intense enough to photoionize gas throughout the inner galaxy. Outflows would heat and expel gas, suppressing star formation. These effects are observed in other galaxies with active nuclei. The Milky Way, with its dormant SGR asterisk, is the quiet version of what many other galaxies are in active states. Understanding SGR asterisk in its current state is understanding the physics of black holes across the universe. The scientific program motivated by the 2019 flare is ongoing, and the instruments being built and planned for the coming decade will transform what is currently a partial, suggestive picture into a comprehensive understanding. The Next Generation Event Horizon Telescope (NGHT) is a planned expansion of the existing global network. Additional stations in Africa, Asia, and the Southern Hemisphere will fill gaps in the current configuration. A space-based DHT station has been proposed for the longer term. The science goal: a true movie of SGR asterisk secretion flow, images taken close enough in time to track plasma structures through multiple orbital periods. Gravity Plus is a planned upgrade to the Gravity instrument, extending its sensitivity and sky coverage, enabling improved measurements of star orbits and plasma hotspots with even greater precision. Gravity Plus will potentially detect the spin of Sagittarius asterisk through the subtle orbital precession it produces, one of the fundamental properties of the black hole that remains unmeasured. In X-rays, the Athena mission, planned for launch in the early 2030s, will provide dramatic improvements in sensitivity and spectroscopic capability, enabling detailed spectroscopic studies of SGR asterisk flares at X-ray wavelengths. The S to periapsis test will occur around 2034. If the S to stellar wind contribution hypothesis is correct, the next S to closest approach should produce a similar episode of elevated activity approximately 1 year later, around 2035. Having the ingot, Gravity Plus, Athena, and JWST all operational by that time would allow the most comprehensive characterization of any such episode ever achieved, a direct observational test of the physical model. This is the scientific agenda the 2019 flare has motivated. a decade of development aimed at understanding one extraordinary event and what it tells us about the nearest supermassive black hole. Why is Sagittarius asterisk so quiet? This question, the flip side of the 2019 flare mystery, is in many ways the deeper one. Understanding what causes occasional episodes of enhanced activity requires understanding the baseline state, why SGR asterisk accretes at such a low rate, why it radiates so inefficiently, and why its dormancy is so deep given the richness of the surrounding gas supply. The galactic center contains an enormous amount of gas. The stellar winds collectively supply several thousand solar masses of material per million years. If it were all accreted, SGR asterisk would be a moderately luminous AGN. The gas is there. Why doesn't most of it fall in? The answer involves a competition between inflow and outflow, between the forces drawing material toward the black hole and the forces expelling it. As gas flows inward in the hot RAF, it gains energy from viscous heating and magnetic processes. This energy inflates the gas, raises its pressure. The gas in the outer parts of the flow has enough energy to escape. Only a small fraction at each radius falls further inward. Simulations consistently show that the mass accretion rate at the event horizon is much lower than at the outer boundary because so much has been expelled at each intermediate radius. The dormancy of Sagittarius asterisk is not a permanent condition. It is a dynamic equilibrium, one that has persisted for perhaps millions of years since the activity that produced the Fermi bubbles subsided, but one that can be perturbed by the right combination of external inputs, a change in the magnetic field configuration, an injection of denser gas that is harder to expel, a change in the angular momentum of infalling material. Any of these can shift the balance and allow more material to reach the inner accretion zone. The 2019 flare is a reminder. A perturbation, a brief departure from equilibrium. Return, one final time, to the night of May 13, 2019. The telescope dome on Mauna Kea is open. The adaptive optics system is running. The detector is accumulating photons, the ancient light of the galactic center, arriving after a 26,000-year journey through the galaxy. The number on the screen is wrong. Not catastrophically wrong. Not obviously, alarmingly wrong. Wrong in the quieter, more unsettling way that genuine anomalies present themselves. A value that sits outside the expected range, that survives every calibration check, that grows more wrong with each successive exposure as the night deepens and the data accumulates. The photons that arrived at the Keck Observatory on May 13, 2019, left the galactic center in the year 24,019 BC when human civilization consisted of scattered hunter-gatherer groups, none of whom had yet invented writing, agriculture, or the wheel. The light spent 26,000 years crossing the galaxy. It arrived on a Tuesday in May. A graduate student noticed the number was wrong. This is not a coincidence in any mystical sense. You can only detect what you are equipped to detect. The 2019 flare was the first to be observed not because it was the first to occur, but because it was the first to occur after 20 years of monitoring had established what normal looked like. Sagittarius asterisk is in many ways the inverse of the heliosphere story. The heliosphere is defined by its protection, its quiet role as a shield noticed only when something threatens to breach it. Sagittarius asterisk is defined by its potential, a quiet monster at the center of the galaxy, noticed most when it briefly reminds us what it is capable of. 4 million solar masses, an event horizon 12 million kilometers across. Orbiting it, dozens of massive stars on tight elliptical paths, feeding it with their winds. And occasionally, not often, not on any regular schedule, a brightness surge. A flare. A reminder. Something happened there. We are still figuring out what. We are the first generation of humans to have the technology to watch the heart of our own galaxy in real time. The black hole has been there for billions of years, accreting slowly, flaring occasionally, maintaining its quiet dominance at the galactic center, indifferent to the star systems orbiting far away at the galaxy's edge, one of which happened to produce. After 4 billion years of biological evolution, creatures with infrared cameras and enough mathematics to interpret what those cameras detected. On May 13, 2019, those creatures saw something they hadn't seen before, and now they can't stop watching.